Hey there, it's February 6, 2018. This is the third in a series of discussions of Gauss's fundamental theorem of algebra. And what I wanted to do to start with today is to come back to what we ended on last week, where we had some homework to draw up on a piece of paper, choose a vector 1, or a length or a number 1, where we draw 1, choose two A numbers, choose two A values, draw out 1A, a squared, a cubed for each of those, and then come up with a general idea of what it would mean to have a to the nth, so an arbitrary power of a number on the complex plane. So does anybody have any drawings to hold up to the camera to show? Anybody do that?
I had some difficulty with that, but okay, there's somebody showing something here.
Okay, so we've got ones over in the corner. Got it. Okay. Could you draw 1 on your main diagram as well? So it's with a and the a squared. Mm-hmm. Jose, were you going to show something? Oh, okay, here's Rick again. Okay, so we got 1, got a squared. Looks like a cube's kind of, it's big, it's off the paper. Okay, all right. Anybody else have a drawing they can show? And then Chance, let's talk about, okay, here we go. 1, a squared, a cubed. Okay, that looks correct. So far, both drawings look good. Any more? So Chance, what were you were saying something? Can you say more?
I was just saying I didn't get too far in it. I tried to do some stuff today, and I didn't get too far. I think I was trying to make the drawing line up on the graph paper, and it ended up making it more confusing. So I tried to get rid of that and just rely on the cosine and radius, but I sort of was tripping over myself, so I didn't figure it out.
Okay. You have something partially figured out that you could show? Well, so we got some pictures there. Did anybody get a general idea of what, let me switch cameras. If we've got, there it goes. So if we've got 1, and then we've got some number a, and then we had a squared, each of these could also be expressed as a length and a direction. So, for example, 1, we could say, well, it's got a length of 1, and I'm probably writing that too small, and its angle is 0. For a, let's say it's got a length, I'll just write r. So length is r, however long it is, and its angle, let's say it's phi in general. So phi would be this amount of rotation from 1 up to a. And then the length of a is r. So a means this length, but also in this direction with relationship to 1. If we want to talk only about its length, we can use another letter r. So it has a length of r and an angle of phi. when we square a number, so that means 1 is to a as a is to a squared. The length of a squared, what's the length of a squared?
Well, I thought it was 2r plus r sine of 2 phi.
Can you hold that up your sheet so we can see how that looks? Okay. Could you describe it or use the look at the picture and help us work through where that came from?
Yeah. I can't see it now to say it, but I projected the I made a square out of, or a rectangle out of it, and I projected the end of it over to the y-axis, which I then called r times the cos of 90 minus 2 phi, which comes out to the sine of phi. And then that's that component, and then the other component is just twice times r. So I took the well, I don't know. I took the the length of it as just the normal 2r, and then I took one component. I don't know how I came up with that really. Oh. And I'm getting my phi's and my thetas confused here. So I split it up into a vertical and a horizontal component.
Okay, let's okay, so that's any other thoughts about this? Any other ideas about the length of, going back to the question here, what's the length of a squared? In other words, what's the length of this this green line here? We've got one. Okay. Number 5. Number 5. Preston, you were going to say something? Oh, sorry. Yeah. Okay. I'd mute my. Okay. So let's. If you're not speaking, please mute yourself. So again, the question we've got is, what's the length of that green line here? What's the length of the number a squared? So the numbers include a direction. 1 is over here. It's this motion. A is a certain distance, and it's got a certain orientation. And a squared has got a certain distance and a certain orientation. I want to break up the a squared into 2 aspects. How long is it? And how much is it rotated? Look at those separately. So what is the oh, did you want to say something? Toby, if you're speaking, I can't hear. So what's happening right now is there's really bad feedback.
There's really bad feedback.
You're on Google, but your microphone isn't working apparently. Maybe try unplugging.
Maybe try unplugging.
Okay, well, I'm not sure if you're trying to say something, but can't hear you there. So let's just go ahead with this. So again, the whole idea of what multiplying means that the product is to one of the factors as the other factor is to 1. So let's take a look at squaring using the numbers 1 and 3 for starters. So very basically, 1 is to 3 as 3 itself is to 9, because there's a tripling going from 1 to 3, and there's a tripling going from, here we go. There's a tripling from 1 to 3, and there's a tripling from 3 to 9. So 3 times itself, we apply its difference, the way it relates to 1, we apply that to itself. Now, when we're looking here at the relationship from 1 to a, that's the same as the relationship of a to a squared. So 1 to a, whatever that relationship is, it got maybe twice as long and went up maybe 30 degrees. If a was 1, we'd again make it twice as long and move it up about 30 degrees to get a squared. 1 is to a as a is to a squared. So looking at the length from 1 to a, perhaps it's doubling. Maybe r is 2. If that's applied again to itself, you would have doubled again. You would have gotten 4 for the length of a squared. Or if a was 3 times as long, a squared would be 9 times as long. In general, its length is r squared. That's all. In terms of the lengths, 1 is to r as r is to r squared. Then if we look at the angle here, so if the angle of rotation to get from 1 to a was phi, what's the total amount of rotation to get to a squared? Madeline, can you? Hold on. Okay, we can't start a new call that way. If we do it, if you try to start, Madeline, if you'd like to join, just join. Use the link that I emailed if you want to add another device to this. If you start a new call, it won't be recorded. So maybe we should just take a minute here and get our connection working, huh? Okay, so Toby's phone or something is okay. Okay. All right. So again, I haven't been able to hear anything from anybody in Dresden yet. So if you're trying to say something, it's still not working. But Toby, you were muted in Google when you were last trying to speak. So. Can't hear you, Jose. No. Did you unplug the connection? Okay. All right, so I'm just gonna maybe, I don't know, maybe type things in the chat or something. I don't know how we're gonna communicate because it's not working so well. You know, one of the things is to change which camera is being used with the gear in the Hangout, but you're on a tablet, so maybe that's different. I'm gonna continue with this and like wave your arms or something if you've got a question, or we'll figure this out somehow, guys. So going from 1 to the number a, we got longer and we rotated an amount phi. Well, if a is our new 1, then we're going to extend its length and we're going to rotate it the same amount. In other words, this is just another angle phi right here. And overall, a squared has a length of r squared and an angle of 2 phi. That is, the angle has been added up and the angle's been added and the length has been squared. So let's go ahead and do this with 2 numbers, a and b, and we're going to multiply them, and we're going to figure out what the product of them is, okay? So let's say again that we've got 1. We've got our number a. Let's say it's out at a distance of r. I can hear you.
Hi.
Hi, hello. Okay, the audio is working, good. Okay, so a is out at a distance of r, and it's at an angle of phi, let's say. I want to do is multiply that by b. Here's b. Let's say it has a distance of big R and an angle of theta. What I'd like to do is, if you draw something like this on your paper, let's work out what a times b is, very similar to what we did at the end last time. And we'll figure out if we can express that product, a times b, in terms, first do it just visually or graphically. Create the distance a times b, create the number a times b, and then we'll see if we can express it in terms of these the lengths and rotations of each individual number.
I'm a little confused about your notation here. It looks a small r, comma, phi, and then a big R. That's a comma. Those are 2 coordinates then?
Those are 2 numbers that I'm going to use to describe it, yeah.
Okay.
Yes, it's a comma. In other words, the distance of b, the length of this line, is big R, and its angle is theta. The length of the number a, not the number a, because the number itself also includes the amount that it's rotated with regard to 1, but its length is r, and its angle is phi. What I'd like to know is what's a times b. And then we can express it in terms of these r's and phi and theta. Let's see if we can do that. But first, go ahead and just draw it on the paper. There's something very similar to what we had done last time. I'll show you what we did last time. Remember, we had a couple examples of multiplying 2 different numbers. Here we multiplied a times b to get the product over here. And we saw that 1 was to a, just like b was to the product. That was one example. So basically do the same thing again here. Oh, great. Chance sent a little picture, which I will share with everybody. Oh. Chance, I don't know why Google is, oh, cool. I'm going to share that what Chance just drew.
It's very wrong. I finally figured out how to share my homework. That's all. But it's after you declared. Wow, it's so funny. You clarified everything now, so it makes a little bit more sense. But I just wanted to share my homework, just what I had so far. Yeah. Anyway.
Okay. Yeah, your homework. The angle looks right, and then so yeah, the length should be longer on a squared, but the amount of rotation looks about right.
Yeah, I just realized as you were talking that I wasn't applying the same relationship to 1 and A as I was to the relationship between A and A squared. I didn't fully register that last time, but now it makes more sense. It's
Oh, okay.
actually a question. It's the question I wrote when I was doing the homework. Um, is it the same? Anyway, I just figured it out a little bit more as you were talking, so it clarified some stuff that I had.
Okay. Okay. Well, that's good. So, okay, so for the, oh, let's get another message here. Oh, okay. I don't know why Google's giving me trouble. Okay, I'm going to put up Jonathan's homework. Share that now. Okay. So, okay, so here we've got one.
That's
Okay.
not my homework. That's
Oh, this is what we just did. Oh, right. Go ahead. Good, good. You wanna explain that?
Sure. Yeah, just from the definition that Wessel invented is 1 to a rotation by phi, and an elongation by small r. And then b to the product is also a rotation by phi. So the angle is theta plus phi, and an elongation by r, so small r. So the length of C would be big R times small r. I hope that's visible there.
Yeah, I think so. Okay. Right. Yeah, so the angles get added and the lengths multiply.
I
Right.
also sent you 2 pictures of my homework. You can discuss whenever you like.
Oh. Okay, let me have a look at that right now. Good. Okay, good. Okay, looks good. And then here we've got was that oh, you were holding up a piece of paper there, but I don't see it anymore. I don't know what happened to the video in Dresden. Okay, we're really having some technical problems today, unfortunately.
I'm sorry, Jason. We're really having some problems here.
Yeah.
Next time we're gonna use a computer that actually works. Trying to show something, but yeah, it doesn't work the video now.
Okay. Okay.
Yes or not? No.
I hear you fine. Yeah.
And the video?
No, well, there's a freeze frame and among the little squares in the bottom of the screen, it shows what looks like a correct drawing. But okay, I'm just gonna go ahead and I guess I'll do a lot of drawing and talking here because it's hard to, your video is not working. So the product would be about like this. Here's AB. And the length of it, well, so if we look just at the lengths, 1 is to little r, as big R is to, well, big R times little r. So if these lengths were 2 and 3, the length of the product would be 6. So the distance here is big R times little r. And as far as the amount of rotation,
Wait, Jason,
yes.
can you just say that again with the big times little r? A little bit lost there. Oh,
Sure.
okay, wait. So big R is B. Big R E. Is that what you mean?
The length of AB as a length, the length of this line, would be the length of line B times the length of line A. Now, saying that would be because, so like, let's draw two triangles. Here we got one triangle. The one goes out to A. The relationship of this leg to this long leg here is a ratio of 1 to little r. We made a new similar triangle right here. Here the length is big R. So just like 1 got lengthened to R, maybe it got doubled. Well, big R will get lengthened to big R times little r. So this line would also get doubled. If going from 1 to A was a doubling of length, then B to the product would also be a doubling of length.
Okay, I think I see what you're saying. I'm assuming that the relation between A and B is not the same as A to A squared, somewhat arbitrary. The relationship between A and B.
An arbitrary place.
Oh, okay. Okay, now I get it. Yeah.
Okay.
I got a question.
Yeah, go ahead.
I'm going to hold up the diagram. I was wondering to stay with a graphic solution, maybe. I wonder if we could do it in a slightly different way. I'll hold it up now.
Okay, so we see one. Yeah, that looks very similar, right? 1 is to A as B is to A times B. The amount of rotate. Wait. Hold it up again. Now the angle back slightly. The angle phi. Okay. Let's look at those two angle phis. There's a mistake there with the red phi that you've drawn in. Between 1 and A, phi is the angle enclosed between 1 and A. So if it's the same type of relationship, it should also be the angle enclosed between B and the product. You've got it drawn as a kind of an exterior angle over there. Is that difference? Is that clear?
Well, to a degree, yeah. I'm just wondering if you what angle should have been put there, you think? Where because I'm building it on top of it, right? Maybe, should it have been phi plus theta, maybe?
I don't think that angle really, what would that angle be? It seems like it's not very important. Well, that angle would be, I don't know, but it's certainly not phi.
Okay, I'll have to think it through some more.
Let's go through what that angle would be if we want to look at that angle for reason. Okay. Let me redraw what Rick had drawn up there. Oops. No relationship between A and B. They happen to be close, but there's no particular relationship between them. So here we have, using similar triangles, that the relationship from 1 to A is an angle of phi, is also the same as the relationship between B and the product. This is again an angle phi. Rick was wondering what this angle here would be. Well, I don't know what it would be. It would be the same as whatever this angle is, which we never gave a name to. but the angle phi is here. That way it's the same, like 1 is to A. 1 is to A. This relationship, the triangle, is exactly the same as B to the product. Similar triangles. Okay. So if we're multiplying two complex numbers, back here, we multiply their lengths and we add their angles. Getting up to B was an angle of theta, and then we add phi more to get to the product. So I think we've got a couple of things that we're able to conclude from what we've looked at so far. So this is what I think they are. I think that 1a squared, a cubed, would be going from a distance of 1 and an angle of 0 to a distance of r and an angle phi, to the distance of r squared and an angle 2 phi, to the distance of r cubed and an angle 3 phi. That is, if we went up to a to the n, it would be at a distance of r to the n. The length would be taken to that power, and the angle would be multiplied n times. Okay? We also saw, in terms of adding two numbers, so I'm going to write this again in a little bit of a different way, and I think it's okay based on what we've covered. This might make sense, and I want your questions about this if it doesn't. I'm going to go ahead and say that our number A, I'm going to write it like this. R cosine phi plus the square root of -1 times R sine phi. Is that okay? Is that somewhat familiar from before? Draw a picture of that.
Yeah, it's like a plus b square root of -1.
Well, here A is, yeah, we could call it like A plus B root of -1. Yeah. I was using the uppercase A to mean a whole complex number. It's like here. So here's our, let's say here's our number A. We're on a circle of radius r, so coming out here, we have a length of r. So A, well, this distance on a circle whose radius is r, where this is the length of its radius. Does anybody remember what this length is right here? If we rotate up an angle phi?
It must be cosinus of the angle phi times r.
Yes, very good. That's right. R cosine phi. And what is the vertical part here?
It's the sine of the...
Right. Yeah, this length is r sine phi. If we want to include the fact that it's pointing in an upward direction, then we can say overall that A equals r cosine phi plus the square root of -1 times r sine phi. And that's because, remember we had 1 and -1, and the square root of -1 which was half the way to becoming -1, was pointing in this perpendicular direction. So if we went r cosine phi and added square root of -1, r sine phi, that would get us to A. Is that okay?
Yep. Yeah.
Very
It makes. Yeah. It's like driving directions. It's not like Yeah. You're describing it more like directions to a location as opposed to a unit of measurement or an area, like a fixed entity.
Yeah, we're dealing with numbers as all motions on the plane. So yeah. Yep. Okay, good.
Difficult for me to do. I have to force myself to think that way. I keep wanting to visualize concrete objects, but yeah, I see what you're doing.
Okay. So what I want to move to now with this is to take a look at what squaring complex numbers can teach us about sines and cosines. So let's take a look at the at Gauss's paper for a minute here. So pull that out and let's have a look at section 13. And we're going to let me share it on the screen here. Okay, so let's go ahead and read section 13. Would anybody like to read it?
I can read it. Number 13, or?
Yeah.
A lemma. Let m denote any positive whole number, then the function sinus phi multiplied with x to the power of m minus sinus m phi multiplied with r to the power of m minus 1 multiplied with x plus the sine of, in brackets, m minus 1 times phi multiplied with r to the power of m is divisible by x squared minus cosine 2 cosine phi multiplied with r times x plus r squared. The proof: for m equals 1, the function is 0, therefore divisible by any factor. For m equals 2, the quotient is sine phi, and for any greater value, the quotient will be sine phi multiplied with x to the power of m minus 2 plus sine 2 times phi multiplied with rx to the power of m3 plus sine 3 phi multiplied with r squared multiplied with x to the power of m minus 4, etc. Plus sine, in brackets, m minus 1 times phi times r to the power of m minus 2. It is easily confirmed that the product of this function multiplied by x squared minus 2 cosine phi multiplied with rx plus r squared is equal to the given function.
Okay, good.
I think it would be fun to actually calculate that.
Yeah, that's what I want to do this time. I want to actually go through and we're actually going to really do this like he said. So let's try, for the, we got two things here. We've got that function that's actually written in the lemma, and then we've got his proof. So for the proof, he says that for m equals 1, the function is equal to 0. Let's make sure that Gauss is right, that he didn't make a mistake. Maybe we'll be the first ones to find it. So let's try it out. So everybody go ahead and write that function, and everywhere there is an m, write 1. And let's see what we get. I'm going to do it on a computer here. Revealing. Anyway, once anyone gets it, go ahead and just say how it's coming along.
M equals 1, right?
Yes, please do it for m equals 1.
Hey, what's that program called?
Oh, this is Mathematica.
Say again?
This is Mathematica.
Okay.
Mathematica, it's called.
Jason,
Yes.
is Gauss using degree or radian as phi, value of phi?
Well, for our phi, it doesn't really matter so much.
I do it now, but I'm doing the 2 already.
M equals 2. It'll work either way, whether you're using degrees or radians.
No, if I use a degree, sine of 1 degree is really small, but sine of 1 in radian is much bigger.
Well, so are you using a specific value for, you're using a specific value for phi?
Oh, sorry, I made a mistake there.
Okay.
It's a sine m minus 1 times phi.
Yes, right. That all goes together. Sine of m minus 1 times phi.
All right, okay, good.
Okay, so I did the first part of the equation right before it says is divisible by x minus 2. In the first part of the equation, I got phi times r. Or yeah.
What did you so it has like 3 things in it, and you round up with only 1 at the end, which that sounds plausible. Can you describe how the rest of it disappears?
Well, if you look at sine times phi times x to the m power, that in and of itself, if m equals 1, right? Yeah, so what I got was sine times phi times x minus sine times phi times r to the 1 minus 1 power, which is r to the 0 power, which is 1, right? So I got sine times phi times 1x. I'm probably jumping around too much. I don't know if this.
No, you go ahead.
The way I'm
why don't we do it? I'm ready. Why don't we go through it again? And this time I'll write as you're saying. Your video is not up. Your video can see it together.
Okay, yeah. Let me.
So start back. Start back at the top.
Yeah. I can send the picture I have for the simplification of the equation.
Why don't you just keep talking? What you're doing is perfect. I should have been writing.
Okay. So then I got yeah, so I got 1 second here. Okay, so I got okay, starting from the beginning, I got sine times phi times x minus sine times phi times x plus phi times r. When I put the 1 in for all the m's.
Okay. So can you explain the last term? Just phi times r. Can you talk us through, please?
Yeah, phi times r is because yeah, so how did I get that? So I got where it says sine in the second part of the original equation, where it says sine sine phi, sine times phi. Sorry, let me just pull it up here. Yeah. So it's sine times phi times x to the m power is the beginning, and the second part is minus sine times m times phi.
Let me just interject for a moment. This isn't sine times m times phi. Sine is a function. It needs to be given something to do its work.
Oh, I see.
This means the sine always needs to know an angle. Sine by itself isn't a number. Nothing.
Can you mute yourself?
Yeah, the chance of a big echo when I'm speaking. Unless you mute yourself.
Yeah, one second.
I'll mute you for a second. Okay. So let's just talk about what these words are. So let's say I had so sine is a function. Here's an example. Let's say I had something called double. And if I double a number, I get its double. So double, we could call it a function. You need to give it something to do its doubling with. Chance, you may have seen this in ActionScript when you do you can set in After Effects, you can, for your parameters and things, you can give them numbers, or you can make it be a calculation based on like your frame number or something like that. And you might put in sines or cosines or anyway.
Yeah, I know what you mean.
Okay, great. So doubling, so by itself, double, it doesn't mean anything. It means this is an action that needs to have a subject for its action, to do its action upon. So, Chance, tell me what would this be? Double of 3 times x. What would that be?
My guess would be 3 squared times x squared.
So doubling, if you doubled 7, we got 14. We just had we had multiplied it by 2, in other words.
Aha, okay, yeah. So then it would be 3 times x plus 3 times x.
Exactly right. Which we could also call 6x. But yeah, right, we doubled whatever we gave it. So coming back to what we're looking at right now, so the way that this gets treated, when we see the sign of m phi, it's the sign, when we read it out loud, we say of, because it's like you might say, well, the double of 7 is 14. The sine of some angle is a relationship between 2 legs of a triangle. So here we've got the sine of m phi. That means that also in the third term, this is really what's going on. We've got the sine of what? The sine of how much? The sine of m minus 1 phi. So, Chance, I'm going to mute myself, and I want you to talk this through. I think that the first 2 are cool, but please talk through what you think the third term would be. And it might change now that we've got this implied red bracket here. But tell me what you think the third term of this is when m equals 1.
Okay, so I think it'll be sine times 0, right?
Sine of 0.
Oh, sine, that's right. Sine of 0. That's right. Sine of 0. So then, times r. So wait, is that the whole equation? The sine of 0 is, I want to say, well, I don't know, 0, or I'm not sure how to equate sine of some number.
Okay, so let's go ahead and find out what the sign of this number is, specifically the sign of 0. So let's make a drawing. So again, what is the so the sign? Did somebody want to say something?
I would just have a proposal, but I guess you do it now.
Oh, okay.
It's the drawing of the circle.
Okay, yeah, that's right. Okay. Well, if you ever get your video working, you can do an example. How about that, huh? You want to show it? Okay, great. Good. Can you talk us through that, Toby? You're muted right now. Can you talk us through it?
Yeah, if you imagine, wait. If you imagine there's an angle at this line here, and this angle phi would be 0 here, then the sine, because the sine is the height of the angle, would be 0, so it would be here, and the cosine would be maximum, it would be 1.
Toby,
So,
can you hold the camera a little bit further away, please?
better?
Yeah, a little bit more.
So the cosine would be 1 and the sine would be 0. For the angle phi 0, the sine would be also 0.
Oh, sorry, I had myself muted. Yeah, yeah, that's right. That's right. Now, I guess the real question is what Chance thinks about that.
I think that makes perfect sense. That was like very ingenious the way he described it. That's perfectly clear.
Good. So then let's return to what we've got here for this equation, Chance. And so we had sine of phi times x minus sine of phi times x plus the sine of 0 times r. What is the sine of 0 times r going to be? What will that give us?
I want to say 1, right? Because the sine of 0 is, oh no, it'll be r, radius.
How much is
Sine
the
of
sine?
zero- The sine, oh no, the cosine is radius, but the sine is 0. So it would be 0 times radius, right?
Yeah, and how much is?
It would be 0. The sine of 0 times radius equals 0. I can't hear you if you're talking, Jason.
What do we get with the first two terms?
We get 0.
Right. Yeah, good. So Gauss had said here in this section that if m equals 1, then the function equals 0, which we just verified. We plugged in 1 and we got the whole thing turns to 0. So he says that if m equals 2, the quotient is sine phi. So please work through what is it. This is about to get really tough, but work that through again when m equals 3. I'm sorry, m equals 2, and see what you get.
Is sine of 2 phi, is that equal to 2 times sine phi times cosine phi?
Yes, as a matter of fact, it is. It is.
Okay. It was just a guess because then it would fit, but maybe you can show us how we can see it.
Yes, exactly. That's where we're gonna end with today. Is with that actually.
I'm sorry.
Oh no, that's fine. It's good to get the preview. Now, are you going to be able to show things, Jonathan? Are you going to be able to have video? I want to give everyone a minute to work this through, and then I'd like you to describe why you asked that question or how it comes up.
Sure. But maybe I will send you a picture again and then describe that. Maybe that's better.
Okay. All right. Let's see. If you could send the pic, for whatever reason, my Gmail's not working well on blowing up Hangouts chat images. If you can email it to me instead, it'll be easier for me.
Sure.
I'm doing it by long division, but I got kind of stuck. It looks like it's going in the right direction though.
Yeah, there's if you do it that way, that's right, and you're gonna end up finding something that doesn't quite work out. That'll lead you to Jonathan's question. So let me just talk for a moment about what quotient means. So quotient, and that's the word that means what you get after you divide something. So 14 divided by 2 equals 7. So in terms of our vocabulary, 2 is the divisor, and 7 is the quotient. So that's just the words. When you multiply a quotient times the divisor, you get back the initial number. So 7 times 2 brings you back to 14. What Gauss is saying, it seems that he says that the quotient will be sine phi.
I think I got it, except that to do it, you have to prove that the cos of phi times the sine of phi is equal to the sine of 2 phi.
Yeah, almost. That's very close. Jonathan's going to go through it in a moment. I just want to write one more thing about the words and then go for it. So the quotient Gauss is saying is sine phi. The divisor, he says, is x minus 2 cosine phi rx plus r. So, okay, it's got some things written out here. So supposedly, the quotient times the divisor should give us this. So let me pull up Jonathan's pictures. Okay, Jonathan, I'm going to show your picture, and then if you want to go ahead and describe what you did.
Mm-hmm. Sure.
All right.
So here in this block, you can see, let's say, 3 lines. And the first line, I just put in 2 for m. As is pretty simple. And then in the next line, I ordered it a little bit. And then I compared it to what Gauss wants to divide it by, the so-called divisor. x squared minus 2 cosine phi times rx plus r squared. And so I figured out that I'm still in the second line.
Oh, okay.
And so I figured out something is pretty similar. So we have the term x squared in the beginning. We have the term r squared at the end. In the middle we have rx. So that's pretty similar, but we have always something with sine phi. So and then I thought, if I can somehow transform the term sine to phi, so that I can like if you can put up the second picture. Right, thanks. In the third line, this is where I want to come to extract from all parts of this equation. I want to extract sine phi, and yeah, therefore I had to transform the term sine 2 phi, which I showed in the first picture. And yeah, and then I thought maybe it is the case that if I wrote in this picture in the first line, if it is the case that sine 2 phi equals 2 times sine phi and cosine phi, then it's possible. And I did a simple calculation and it fit twice.
Yeah.
So I suppose that's a good sign that it could fit. And then when I divide, I think that's pretty clear. If not, please ask a question. If we divide the last line with this divisor that Gauss gave us, which Jason showed us last time what it actually is. If we divide it by that, then only sine phi remains.
Jonathan, can you explain the cosine again? I'm not sure what that came from.
Yeah. Jason, could you jump to the first picture again? Right. So Chance, if you can see here in the second line, there's a term in the middle, Rx times sine 2 phi. And we have that is different to the other two terms, left and right to it, where we only have sine phi. So to be able to extract sine phi from all the parts, I have to transform this middle term. Is that clear, the idea?
Yeah, that part is very clear.
Okay, good. So in order to transform this term sine 2 phi into a term sine phi, I had to really think back. Yeah, and in my case, I thought back into what we did in university. So you have to always be creative and transform equations back and forth. Yeah, and then I thought maybe it's possible to somehow combine this thing sine 2 phi with a cosine, because Gauss gave the hint that we have a cosine which we want to divide it by. So anyway, I just guessed and I hit it right. What Jason, if you can show again the second picture. Thanks. So Chance, look at the first line. I think that 2 times sine phi times cosine phi equals the term sine 2 phi. And then I put instead of sine 2 phi on the first picture, I put the left term in, and the second line comes up. Is that clear?
The equation's clear. I'm just trying to. I guess you just took a leap of faith and looked at the result that he got, because I just don't see where. I mean, I didn't learn that in university. This whole cosine equals sine thing. So that's probably some more basic fundamental stuff that I just don't have under my belt. But I'll take your word for it for now.
Well, this is what we should really prove. If that's really true. Yeah, Jason has already an idea how to do that.
We're going to see whether that's really true or not, for sure.
Without going through a big geometrical proof, I just did it for 30 degrees, and it is true for 30 degrees.
Mm-hmm. Yeah. So, right. Yeah. So the quotient times the divisor could be the same as what Gauss wrote if the sine of 2 phi, this might be a little bit repetitive, but I'm just going to write it one more time. I'm going to write the quotient times the divisor. So sine times this whole thing. Sine phi x squared minus 2 sine phi cosine phi rx plus sine phi r squared. And then comparing that to what Gauss gave us when m equals 2.
Sorry, Jason. I know I'm asking a lot of questions. I just you said in the second part of your equation minus 2 sine phi cosine phi. So the 2 has to come before. I'm trying to. Why wouldn't it be the sine of 2 times cosine phi rx?
Well, it couldn't be the sine of 2 cosine phi. You can only have the sine of some kind of an angle. In terms of why did I write the sign after the 2, you're right. I just did that without explaining it. It's because it's just sort of customary that you write plain old numbers in front of things that involve letters and variables.
Okay, no, that's fine. I don't know much of the basic rules, so I'm asking a lot of like kind of silly questions here. But yeah, okay.
It's a question you had. It wasn't silly, because say, well, why did? So it's a reordering. I snuck the sign in right here instead of putting it in front, but that's just for a convention that the numbers come first, but no particular meaning to it. So then if we compare what we get to the to this function, so this is the same, sine phi r squared, this is the same. Look at the middle term, Rx is the same. And then, like Jonathan said, this would be true if the sine of 2 phi is 2 sine phi cosine phi. And we will not take that for granted, and we will now look at why that's true. Because if it were true, then what Gauss said would be right. That's our next task, is to figure out what is the sine of 2 phi and see if it really does equal the 2 sine phi cosine phi. So I'm going to go ahead and draw up a picture for that now to help us start posing that question, unless there's any more. Are there any more questions about this part before we move on to that drawing? Okay. I'm just going to write on the top of the page what it is that we're hoping to find again, just so we don't forget. So we're trying to find out whether this is true, that the sine of twice an angle is 2 times the sine of the angle times the cosine of the angle. So we're trying to get. So let's go ahead and draw up a, let me get something to draw a nice circle. Okay, so let's say that here's our angle. I should really get a ruler and make the lines nice too, shouldn't I? Let me do that. Okay. So, should have used a bigger angle, but too late. We'll go with this, it's fine. Okay. All right, so we've got our, and please draw one of these yourself. So let's say, you know, here's our angle phi. Here's our angle 2 phi. So the sine of 2 phi, this vertical distance right here. Ugh, bit of a mess. Okay, so we want to, what we're looking for is the sine of 2 phi. Now I'm just going to draw a couple of more lines here as a way of a hint and see if any ideas come to you, okay? Draw a couple other lines. Here we go. Wow. Should be using a different pen. I'm sorry, that got kind of messy. I'm going to do it again. I'm going to use just a bigger, since we only really need one quadrant of the circle, I can make it a little bigger too. That looks terrible. No. Okay, there we go. That's fine. So make our angles here. Angle phi, angle 2 phi. Again, here's our sine of 2 phi. And then here come the hints. So let's I've got, here's a phi, here's a phi. So let me ask some of the other lengths that are drawn on this diagram here. What is what's the length of this purple line right here? Anybody know?
Sine of
phi.
Yes, it's the sine of phi. We took a look at this. We'll turn it on its side a little bit so that we only have, we sort of just have this triangle all by itself. Then we got right triangle, and it's this angle is phi, so this purple line would be the sine of phi. Yes, that's right. Let me also ask what this green length is. How long is the green length here?
Cosine of phi.
That's right. That's right. So this will be tricky here, perhaps. What is this vertical purple line's length?
It's also sine.
It's a sine. It's a little bit different than totally being the sine of phi, because this would be the full sine of phi. Excuse me, this would be the sine of phi, the right side of this plastic here, right? Because then I'd be starting from the circumference of the circle and drawing a line straight down. But for this purple line, I didn't start out at the circumference. I started in a little bit, right?
I was wrong. It is sine phi of the cosinus.
Yeah, very good. Very good. Exactly right. Because on the triangle where the hypotenuse isn't the full one, isn't the full radius of the circle, but is the shorter length of cosine phi, on that triangle, it's the sine. So it's the sine phi times cosine phi. That is the length here. Okay. One more step.
Oh, wait, Jason, sorry, I just trying to follow that last step.
Last step.
You said it's the sine phi times cosine. I don't quite follow that. Can you just say that last part again? I think I was writing something, so I was partially paying attention. I think I missed it. I didn't quite get that.
Yeah, I'm going to generalize it just a little bit, and then we'll be able to apply the general concept to this, and it'll be no problem. So here's a triangle. It's got an angle of phi. It's a right triangle. And so let's say that this length, let's say I measured it, well, let's say it's 14 centimeters. This height right here, we couldn't really just say it's the sine of, also let's say that phi is, let's say it's 30 degrees. Here's the thing about what the sine of an angle is. So the sine of an angle, and this is always true in any right angle you ever have, any right triangle you ever have. We've got the hypotenuse, the side adjacent to the angle, and the side opposite the angle. The sine of an angle is always the opposite side as a portion of or divided by the hypotenuse. So on this triangle, this height right here, it's not just the sine of 30, because there's a lot of triangles that have 30 degrees. This is a triangle that's got 30 degrees. If I stopped right here, this is a triangle that's got 30 degrees. If I drew it out here, if I drew it way out, you know, that would still have a sine of, that would still be 30 degrees. So if I want to know specifically what's the length of this side on this triangle, not some other one, it's not just the sine of 30 degrees, it's the hypotenuse times the sine of 30 degrees.
Aha.
So among the many triangles that have an angle of phi, I could have drawn the line down anywhere. Here. Could have made a whole bunch of right triangles that have an angle of phi down here in their corner. But the specific one that we chose to draw down has a hypotenuse of cosine of phi because it was made from this triangle. And this time there's no number in front of it. That's because we're saying that the initial hypotenuse is 1. We call the radius of a circle 1. Then it's okay when we're just write cosine of phi, what it really means sort of inside is 1 cosine of phi. But when there's 1 of something, we don't usually write the 1 in front of it. We just wrote the cosine of phi. So that's why this height is the sine of phi times the cosine of phi, because it's got a sine of phi, but we have to multiply it by what's the size, what's the hypotenuse of the triangle that it's drawn on. Is that okay, Chance?
Yeah, somehow. I couldn't explain what you said again, but it makes a certain amount of sense.
Okay.
I think that's good enough for now, though. I see the relationship now. I didn't see that before. So yeah, it makes more sense than it did before.
Okay. We can always talk about it some more again later. This isn't the only chance. So next drawing on here, and then I'm going to wait and let somebody explain what to do with it. I'm just going to draw a hint. So the hint is that the full sine of 2 phi that we're looking for whole vertical length is made up of this part that we already found and this remaining portion. So let's see if we can figure out how long that is. Anybody who has an idea, go ahead and, when you have a thought, go ahead and say it.
I have an idea. I'm not 100% sure, but I will just say it. Because in the small triangle, we know that we know that there must be phi in the higher up corner, the angle phi in the higher up corner. And then I drew the triangle anew, and then I said, yeah, we have to calculate the cosine of phi times sine, and that should be the searched length.
Yes, that's very good. So on this triangle, pulled out all by itself, this side is the cosine. We can look at it like this, perhaps. This is the cosine side of the triangle, and the hypotenuse is sine phi. So like you said, its length is cosine phi times sine phi, or sine phi. So if we put these two together, we've got the one more color. Okay. So our sine of 2 phi is made up of two pieces, cosine phi sine phi and sine phi cosine phi. Put it together, it's 2 sine phi cosine phis.
Aha, good.
So I don't want to go too much longer today. I do want to see if there's any more questions about this, and then I want to show how we can get this using complex numbers without doing any drawing at all. We can find out things about angles and sines and cosines using the complex domain that are actually pretty surprising. And again, remember, the reason that we did this was because we had this, this was the original function with m equals 2, and Gauss said that it could be divided by this divisor, giving the quotient of sine phi. So we multiplied the quotient by the divisor, and we saw that they're almost equal, except the original function is the sine of 2 phi, where the divisor times the quotient would be 2 sine phi cosine phi. And now we know, oh, these are actually the same. The sine of 2 phi is 2 sine phi cosine phi. Okay. So far we've checked it for m equals 1 when it all turned into 0. We checked it for m equals 1 when the quotient was sine of phi. So let me just write it. So here's where what I want to summarize or sort of pause on at this point. So there's two tracks that we can take right now. One is we can keep looking at section 13. We can look at m equals 3, 4. Just start trying it out and seeing what other trigonometry things come up. Does the sine of 3 phi come up? The sine of 4 phi? You can try this out and find out and see what comes up and see what you can prove about it. The other way is to show that the sine of 2 phi is 2 sine phi cosine phi using the complex domain without actually doing the drawing at all. Although it always is possible to draw these things. They're always geometrical. So let me ask, I guess, for a vote. I don't know what your time is like, if you'd like to keep going today, or if you'd like to pause here, and I can write up a couple homeworks, or if you'd like to, this I want to definitely leave as homework. This we could look at in the complex domain. If you'd like to, we could do that tonight, or we could save it for next time, and I could leave a homework assignment to get started towards it. Any preferences? Or if there's other questions about anything we covered.
I can just say for myself, it's a lot to take, and I'm nearly there. I could follow the thing. I definitely need to do a lot of work to really grab it. So for me to leave it here is okay because I really want to study all of this. But we can also carry on. I don't know what others think.
I just have a question of what you when you say we should prove that sine phi cosine phi thing without drawing. I wouldn't know what to do.
Oh yeah, no, I know. I just meant that to indicate like a topic that we could take up. I didn't. There's not been enough covered to be able to just assign that. No, no. I mean, what I meant is I would give like a couple of problems that would make it easier to do it next time. Why don't we go ahead and Toby?
Yeah, I'm ready.
You want to keep okay? All right, let's keep going a little bit more, and then I'll make sure we have a couple of homeworks. So I'm going to put this aside to make sure I remember, and then we keep going, and then Jose, if you want to watch this it has been a lot, Jose. So if you want to remember, like, okay, about an hour and a half in, let me watch this part again. That makes sense. So let me just bring up one more topic. So when we think about what the complex domain is, we were initially given to the idea that the square root of -1 is perpendicular because of our idea of multiplication. 1 is to the square root of -1, the square root of -1 is to 1. Just like 1 is to the square root of 9, as the square root of 9 is to 9. 1 is to 3, as 3 is to 9. Our idea of multiplying. So we got normal numbers and then the square root of -1 direction. It's possible to write a complex number in terms of a distance and an angle. So let's say this is 1. Let's say the radius of this circle, let's say we come out all the way to, let's call it r. And I've got a specific complex number on here. Here it is. So this number, I'm going to call the number z, is made up of two components. So those components are, again, it's the size of the triangle is r. This leg of the triangle is r cosine phi. This leg of the triangle is r sine phi. And I think that when we put them together in the complex domain, we can say that a complex number z is r cosine phi plus square root of -1 r sine phi. Again, r cosine phi as opposed to just cosine phi because the hypotenuse is r. Like this was 14 times sine 30 or the, anyway. And then the square root of -1 because we're going in the upward direction. I want to take a look at two ways now, and this will be the homework, of multiplying, well, maybe we'll just work it through. Two ways of multiplying a complex number times itself. So our complex number is r cosine phi plus square root of -1 r sine phi. That complex number squared, well, we learned from the very beginning of today that when we square a complex number, going back to the picture, when we square a complex number, we square its length and we double its angle. So z squared, I'm going to apply that. I'm going to say, well, whatever it is, I know that it's like, it'll have the length squared and the angle double. The length squared and the angle double. So this is going from one complex number to another by thinking of squaring lengths and doubling angles. It's that way of thinking about it. There's another way to think about squaring a complex number, and that's to actually just multiply it by itself. I'm going to start writing I instead of the square root of -1, just to be a little easier. So, and this is almost going to be like magic as we do this here. What do we get if we multiply this together? I hope I'm writing big enough also. R cosine phi plus IR sine phi, which is what Z is, times itself, R cosine phi plus IR sine phi. So we could keep going through this right now, but I really like the idea of having some homework. So I want to stop here. Make sure there's an assignment here at the end. We'll cover it next time, but I do want everyone to give a shot at this themselves. So here's your homework. So multiply, in other words, get this Z squared, multiply it out. Compare, I don't need to be writing this, compare to the above, and I'll send this in the email too. In other words, we've got two ways of writing Z squared. This way where we just say, oh, we'll square the length and double the angle. And the other way of actually saying, I'm going to square it and do it like an algebra sort of way. If these two things are equal to each other, figure out what that implies. So that's your homework, is use this and tell me two things. What's the sine of 2 phi? And what's the cosine of 2 phi? We did this one already geometrically, the sine of 2 phi. Now you're going to get if you do this, if you work this out, you'll find out what the cosine of 2 phi is. And then you can also try and prove it geometrically, or just you can try it out by testing out some angles and see if what you get works. So I think that will be really fun. So that's one of the homeworks. The other homework is test section 13 with m equals 3 and 4. If you really want to test yourself, you can try it with m equals anything. See in general what comes up. But these two aspects of the homework really go together. You'll see when you work on it. I hope that they're very much related problems. So work on that over the next week. Multiply this times itself, FOIL it. This times this, plus this times this, plus this times this, plus this times this, and compare it with here. And then secondly, go back to section 13 in the paper and try plugging in values of m. We did 1 and 2 today. Try it with 3 and 4 on your own. And if you have any questions along the way, email me. We can do another little call here or there, but that's what I'd like you to do for next time. So let's
All right, that sounds like a good work.
That's definitely some meaty homework, and I'll type up that homework and send it out to the email list. And so if there's any other questions for today, or always email.
Okay, auf Wiedersehen.
Ja, auf Wiedersehen.
Everything. Oh, auf Wiedersehen. Okay. All right. See you next time, guys.